Hello everyone. Today I will be taking you through a demonstration of computing alignments, specifically global alignments between two pairs of sequences, semi-global alignments between two pairs of sequences, and local alignments between two pairs of sequences. I will start by describing what sequence alignment is, talking about score functions which are used to determine how good we consider the matches between two characters, and then I will proceed to describe what global alignment is. I will talk about how it is computed. I will write code to compute global alignment between two pairs of sequences, and also demonstrate how to compute the actual alignment by running a traceback from the alignment matrix. Further, I will take you through the code which will let you compute the semi-global alignment between two pairs of sequences and the local alignment between two pairs of sequences as well. The end of this demonstration, I will show you the results of global alignment between the genome sequence of the COVID-19 Delta variant and the genome sequence of the COVID-19 Omicron variant. Let us get started. The sequence alignment between two sequences, let us call them A and B, is an alignment between A and B as a pair of sequences U, L, such that both U and L are of the same length. Let us call that H. A is a subsequence of U, B is a subsequence of L, and U contains H minus M gap characters and L contains H minus N gap characters. As an example, you can see here the sequence A, if we take it as the word riddle, and the sequence B, if we take it as the word triple, then the alignment between A and B can be represented like this. There is a gap to begin with, and then the letters R and I in riddle and triple are aligned. There is a point of difference between D and P. There is a gap in triple aligned to D, and the letters L and E are aligned once again. So, how do we compute these alignments? We use something called score functions to determine how good we consider matches between two characters are. So, if we pass two characters to this score function, let us call them A and B, we will assign a value to return depending upon what the values of A and B are. If A and B are the same, then this is considered a match, and we like that, we will return a positive value. If either A or B is a gap character, that is not a good thing. That means that there is a gap in the alignment, and we do not want that. So, we will return a negative value. And if A and B are not the same, but however are not gap characters, then we still would like to not have that. So, we will still return a negative value. We can choose these values to get alignments which have specific properties. So, for example, over here I have a function which will prefer mismatches over gaps, and we achieve this by giving a higher negative penalty to a gap as compared to a mismatch. I also have a function which prefers gaps over mismatches, and you can see that over here. I will show in this demo 3 toy examples for each type of alignment, and each of these examples will correspond to using a different score function. Let us move on to global alignment. Given two input sequences, let us call one the pattern and the other the text. The global alignment problem seeks to find an alignment of the pattern to the text with a maximum alignment score W. So, we write it in this form. All this means is that among all possible alignments of the pattern and the text, we want the one which has the highest score. The score of an alignment is simply computed by taking every column of the alignment over here and then adding up the scores for each of those characters. So, global alignment, if we look at one of these strings here as the pattern and the other string as the text, global alignment seeks to find an end to end alignment. So, how do we compute global alignment? We have already seen this in the lectures. We use a dynamic programming procedure where we compute the optimal global alignment score between a prefix of A and a prefix of B, and this is computed as the maximum of 3 possible options. In the first option, we will seek to match AI and BJ. In the second option, we will seek to delete a character in the pattern so that it matches the text, and in the third option we will seek to insert a character from the text into the pattern so that we end up with a match between the pattern and the text. So, given that the size of A is m and the size of B is n, the global alignment score will be stored in the bottommost and rightmost cell in the dynamic programming matrix. Of course, this is a recurrence relation. We need to initialize this somehow, and the choice for initialization depends on the idea that we are computing an end to end alignment, which is to say that if there are any gaps at the beginning or the end of the alignment, we will penalize those, and the way we penalize that is by adding an extra row and an extra column which corresponds to a gap, and we simply store these values. We have already seen these in the lectures, so let us move on to the coding. So, the Needleman-Wunsch matrix function will compute the global alignment for us by computing the dynamic programming matrix. So, let us initialize the dynamic programming matrix, and first let us store the pattern length and the text length, and then initialize a matrix M with zeros. The size will be 1 plus the pattern length number of rows and 1 plus the text length number of columns. Having initialized our matrix, let us initialize the gap penalties for the first row and the first column. We know that this, for the first column, we will be penalizing it in this fashion. Vi0 is the sum of all the mismatches between the first k characters and the gaps. So, in this case the score function will be computed between the ith character of the pattern and a gap character. We do the same thing for the first row of the matrix. and here we will match a gap character with the jth element in the text. Having added the initial conditions for the recurrence into the dynamic programming matrix, we will now fill up all the cells. So, we have to iterate through all the cells. We will go from range 1 up through the length of the pattern. And we will take j from 1 up to the length of the text. So, there are 3 options at any particular stage from the recurrence relation. At I comma j, we can either choose to match or substitute a character, we can choose to delete the character in the pattern, or we can choose to insert a character into the pattern, and we will compute all these 3 scores, compute their maximum and store that in mij. So, the match score is simply the score in the upper left cell added with the score comparing the ith character of the pattern to the jth character of the text. The insertion score will correspond to matching a gap character in the pattern to the jth character in the text, and this will have to be added on to the cell on the left, the score in the cell on the left. Similarly, for deletion, we will look at the cell on the top and add the score which aligns the ith character in the pattern to a gap. We simply have to compute the maximum of these and store them in the ijth cell in the matrix. And that is it. We have got the DP matrix. We will return the DP matrix itself and the final alignment score, which will be stored in the bottommost rightmost cell in the matrix, and that will be indexed by the pattern length and the text length. Alright, now that we have computed this, how do we go back, right? We would like to return something like this, where we have an alignment in between these 2 strings, and we would like to compute that. The way to do that is to use the traceback, right? We start at the bottom rightmost cell and then work our way back up to the top left. The way we do this is by checking which cell, which choice was made to get to the current cell at any given point. So, at the bottom rightmost cell, we would have chosen the option which led to coming to this particular cell. To get to this cell, we would have chosen the highest possible value of the match score, the insert score, or the delete score, and this is the same thing that we will do at every possible step of this traceback. So, let us write some code for that. We are starting at the bottom right corner of the cell. So, let us initialize our index variables. This will simply be the length of the pattern and length of the text. We will store all of these alignments in strings. So, we will initialize these strings as empty lists, one for the pattern, one for something called matches, which I will explain, and one for the text. You will note first of all that I have called these variables reverse alignment pattern or reverse alignment text. The reason for this is that we are making our way backwards along the dynamic programming matrix. So, whatever we store will be in reverse order. So, to get our final answer, we will be reversing these strings. So, whatever we have right now, we will reverse them and report that. Right, now that we have places to store our computations, let us actually run the computation. We are starting at the bottom right corner and we have to make our way to the top left corner, except we do not really want to get into the empty string. So, we will run our while loop as long as either I is positive or j is positive. So, if both I and j are positive, then we have the option of going diagonally up. So, let us store what was the value that we computed had we come to the cell ij from the upper left cell. So, if we came from the upper left cell, that means that we either matched the character at position I in the pattern to position j in the text, or it was a mismatch. Either way, we have a very easy way to compute this. It is simply m I minus 1 j minus 1 plus the score function which matches the ith character in the pattern to the jth character in the text. If there is no way to go diagonally up, then this value should be something very small. So, we will store that as negative infinity. The reason is that we will be looking at the maximum of all of the values that we check here, and we will choose that as the choice that was made to come to cell ij. So, we will store this as negative infinity so that this will never be chosen as the maximum, right. So, it is possible that just I was greater than 0. In that case, there is an option if I is greater than 0 that we reached the current cell by incrementing I, that is to say we went one step down. So, if we did go one step down, then the traversal is vertical. So, let us store it in a variable called vert, and what we would have done is come from m I minus 1 j, and what would we do if we came from m I minus 1 to j? That means that we aligned the ith character in the pattern to a gap character. This of course corresponds to deleting the ith character in the pattern. It is possible that I is not greater than 0, that is to say I is equal to 0. So, in that case we want vert to be negative infinity once again. Lastly, it is possible that only j is greater than 0, right, and if j is greater than 0, then that means that we could have come to any particular cell from the cell on the left. If we are coming to ij from the cell on the left, that means that we have inserted a character from the text, that is to say the j minus we have inserted the jth character into the pattern to get the alignment. So, we will store in left m I comma j minus 1 plus the score function of aligning a gap character in the pattern to the j minus 1th character, sorry, the jth character in the text. Once again, if j is equal to 0, we do not want to be here. So, we store left as negative infinity once again. We do not want left to be chosen if j is equal to 0, right. So, right. So, we have now noticed that we know how to traverse backwards, right. Once we know how to traverse backwards from any particular cell, what do? We need to know which was the choice made, right. So, let us test which of these is actually equal to mij. So, if mij is actually equal to the diagonal value, that means that we either had a match or a mismatch of the ith and character in the pattern to the jth character in the text. So, let us just query that and store that as a variable. So, if this is actually a match, then we want to store that, and what we would like to do is indicate that it is actually a match, and we will use a pipe character to do that. So, knowing that we have come from the diagonal, we will push the ith character in the pattern into the reverse alignment pattern variable. We will push the jth character in the text into the reverse alignment text list, and lastly in the matches list we will append pipe if it is actually a match, else we will simply push an empty character, a space, right. So, there are two more cases, which is to say either we came to mij from the top. In this case we just have to choose different values to be added over here, and we will just do that. Into the pattern we simply append the ith character of the pattern. Into the alignment for the text we will simply push a gap character, because we aligned a gap character to the ith character in the pattern, and in the matches we will simply push an empty string. Again there is one more option. We came from the left, and in this case there is the option that if we came from the left, that means that we aligned a gap character in the pattern to the j minus 1th character in the text, and in this case again in the matches we will simply push an empty string of length 1. Just for sanity we will check that we have not made any mistake, and we will add an else condition and break out of this loop if none of these three are true. This should not happen. Okay. So, now we have actually got the alignment, provided we traverse the entire while loop, we have actually got the alignment. So, let us actually store the alignments in ALN pattern. By reversing reverse alignment pattern. Similarly, we will store alignment of the text in the reverse of the alignment of the text, and lastly we will also store the matches. Right. We will format this alignment into something easy to view. and we will store the text on top. We will store the matches underneath, and we will store the pattern at the bottom. Okay, so we have actually computed everything now. Let's run this. Let's run everything to see that we're actually getting results. So let's initialize all the score functions. Right. The Needleman-Wunsch method has compiled. The traceback method has compiled, and for this pattern and this text, let us see what we get as the alignment. So we get an alignment score of 6, and here, oh, I see there is an error. Okay, I think the error is simple. I have been using the character M instead of D, that is all. Let us compile this once again, and okay, so I may have made a small mistake in this. Let us just quickly check what mistake was made, and instead we will use the logic from this method. Over here, I think the only issue is that I did not return the alignment. So let us compile it once again. Right, and you can see here that we have got an alignment between the text and the pattern. Let us see what happens when we change the score function. Right, we get a slightly different alignment score this time, and here remember we are preferring mismatches over the gap score, and the alignment, okay, the alignment looks to be the same. Let us try it with a function which prefers gaps instead of mismatches, and you will see now that there are slight differences between this alignment and this one. Here additional gaps have been introduced into the alignment, and this is because the dynamic programming prefers to use a gap. It has a lower penalty compared to the other score function. Okay, so let us look at semi-global alignment. So in semi-global alignment, we are trying to find an instance of the text somewhere in the pattern. So right, if this is our text, we are trying to see which substring of the pattern has a high global alignment with this particular piece of pattern, and the recurrence relation remains the same. Actually, the only change is that we do not penalize the gaps at the beginning of the text. So let us write this, let us actually write this initial condition. The initial condition for the column, the first column, does not change, it is actually the same. It is mi minus 1 0 with the score function which matches the ith character in the pattern to a gap, and for the first row we simply set it to 0. So let us see what results we get. So we are able to compile this, nothing else changes in the code, where only thing is we will return the best score and the best index in the last column over here with this logic. We have got the traceback function ready. The traceback function is slightly more complicated because we want to have a easily visualizable output. I will leave that bit for you to go through, and here is the alignment score for this pattern and this bit of text, and here is the actual alignment. You can see here that this bit of text has gotten aligned somewhere in the middle of this text, and this pattern would not be aligned like this if we used global alignment. We would actually see end to end alignment. Okay, so let us try it with a different score function, one that prefers mismatches over gaps, and we see that we get a similar answer to before. Let us see what happens when we run it with a score function which prefers gaps over mismatches, and you can see that the alignment is now different compared to the previous case. In the last example, I would just like to go through local alignment, and in local alignment what we are trying to do is find some substring of the pattern and some substring of the text and check for high global alignment for both of these. How do we achieve this? Well, we add the condition that we do not penalize the alignment beginning anywhere, either on the row or on the column, and we also guarantee that the alignment score never goes below 0. Beyond that, if you are doing local alignment, you need to ensure that there is a positive score for matches. So what you can think of this as trying to match some suffix of the prefix of A to some suffix of a prefix of B, right. So the only thing that changes here is once again the initial conditions, and this time they are easy. The initial conditions for the first row and the first column are both that they are all 0. So let us see what happens when we compile this. Nothing else changes in the code. Once again we go through, we fill the entire DP matrix once again, and we have to compute the traceback just like before, except that we have one additional condition while computing traceback. We stop when we see the first 0, and that is modeled over here by with the additional condition that Dij is positive, right. So let us visualize the local alignment between the same pattern and text that we used in the semi global alignment setting. So in this case you will see that we get this as the local alignment. This is actually a substring of the pattern and the text, and in the setting where we are using a score function which prefers mismatches, right, we get the same result again, and in a setting where we are preferring gaps over mismatches, we get a slightly different result. Okay, so what is an interesting application of this? Typically what we like to do in real life is when we have computed the genomes of 2 species or 2 strains of viruses. So for example the COVID-19 Delta variant and the COVID-19 Omicron variant, it would be nice to know where the differences are, and one easy way to visualize these differences is by knowing what the alignment is in between these 2 sequences. So just to give you an idea, here is what the genome sequence of the Delta variant looks like. So this is a long file, it contains around 30,000 bases, and similarly the Omicron variant also has a genome sequence, and they are slightly different. So let us see what the differences are. So I have the same function here once again, only thing I have a simple score function, and I have the same Needleman-Wunsch matrix and a slightly modified function for the traceback, just so that I am able to print the result better. So here are the first 100 characters of the genome of the COVID-19 Delta variant and the first 100 characters of the genome of the COVID-19 Omicron variant, and you can see that there is some difference, right. So when I ran the alignment, the global alignment, it took me 32 minutes to compute an alignment between 2 strings which are approximately 30,000 characters long. This is a long time, because we need to do this operation many times. And however, you do know that computing global alignment is a quadratic time algorithm, which is a product of the length of the two sequences, and computing the traceback is proportional to the sum of the lengths of the two sequences, and you can see that the time taken was about 0.1 seconds, much faster. So here is the actual alignment visualized. So it starts way over here, a long sequence of gaps followed by a long sequence of matches, and you can see that in some locations like here we have substitutions, and further in other locations you will find gaps, these correspond to deletions, and there are insertions as well. The point of this is to show you that using visualizations like this we can find differences in the genome sequences of two strains of viruses, and this can be helpful in analyzing what types of proteins are produced when these viruses enter a host. I would like to end my demonstration here. Thank you.